Most people think the moon is close, but the space between Earth and the moon is 384,000 kilometers of near-perfect emptiness, enough room to line up 30 Earths side by side. And if you tried to cross that gap at highway speed, you'd still be driving 5 months later, while light itself still needs more than a full second just to make the jump. That is what near means in the universe, and everything beyond this only gets more extreme. Before we go deeper into the true scale of reality, take a moment to subscribe and let's begin. Light travels at 299,792,458 meters per second. At that speed, light circumnavigates Earth's equator 7.5 times in 1 second. A single photon covers more distance in one heartbeat than you'll drive in a lifetime. Yet, crossing 149,600,000 kilometers from Sun to Earth still requires 8 minutes 20 seconds. This creates a fundamental strangeness. We never observe the Sun as it currently exists. Every human who has ever lived has only seen the Sun's past. If our star exploded into nothingness at this precise instant, we'd remain unaware for 8 more minutes. We'd continue seeing its light, feeling its warmth, watching a corpse shine. But here's where it gets stranger. That specific photon landing on your retina right now didn't start its journey 8 minutes ago. It started 100,000 years ago, trapped inside the Sunday. The Sun's core operates at 15 million degrees Celsius. At that temperature and pressure, hydrogen nuclei slam together with enough force to overcome electromagnetic repulsion and fuse into helium. Each fusion event releases energy as a photon, a particle of light. But the Sun is dense. 150 grams per cubic centimeter at the core, 150 times denser than water. That photon can't escape. It gets absorbed by an atom, re-emitted in a random direction, absorbed again, re-emitted again, absorbed, re-emitted billions of times. Physicists at Lawrence Livermore National Laboratory ran computer simulations in 2003 modeling this photon random walk. They calculated that on average a photon takes between 10,000 and 170,000 years to travel from the Sun's core to its surface, a straight line distance of just 696,000 kilometers. Light travels at 300,000 kilometers per second. That journey should take 2.3 seconds. Instead, it takes 100 millennia because the Sun is that opaque. Then finally, the photon breaks free from the solar surface and sprints across vacuum 150 million kilometers in 8 minutes, landing on Earth. On your skin, the warmth you feel from sunshine is older than agriculture, older than the pyramids, older than writing, older than Homo sapiens. That photon began its escape attempt when Neanderthals still walked Europe, when woolly mammoths roamed the tundra, when Earth shivered under Ice Age glaciers. Now multiply this strangeness across the universe. The nearest star beyond our Sun is Proxima Centauri, 4.24 light-years distant. 4.24 light-years equals 40,200,000,000,000 kilometers. If you could drive there at 100 kilometers per hour non-stop, the journey would consume 48 million years. Light from Proxima Centauri takes 4 years, 2 months, 27 days to reach Earth. When you observe Proxima Centauri through a telescope tonight, you're seeing it as it existed 4 years ago. You're watching your own past, seeing that star as it appeared when you were 4 years younger. Sirius, the brightest star in our night sky, sits 8.6 light-years away. We observe it as it was 8.6 years in the past. Vega, 25 light-years. The light you see from Vega tonight left that star in 1999. Arcturus, 37 light-years. You're seeing 1987. Betelgeuse, the red supergiant in Orion's shoulder, sits 548 light-years away. The light entering your eye from Betelgeuse tonight departed that star in 1476, before Columbus sailed to America, before the printing press spread across Europe, before the Protestant Reformation. And Betelgeuse is close. Astronomers discovered in 2019 that Betelgeuse has been dimming, possibly because it's approaching supernova. If Betelgeuse exploded yesterday, we wouldn't know for 548 years. The explosion could have already happened. The blast wave could be racing through space right now, but the light hasn't reached us yet. When it does, Betelgeuse will suddenly become brighter than the full moon visible during daytime for weeks or months before fading. People will look up and say Betelgeuse just exploded. Wrong. Betelgeuse exploded 548 years before we saw it. We're just receiving the news. Polaris, the North Star, sits 433 light-years away. Look at Polaris tonight and you're seeing 1591. Shakespeare hasn't written Hamlet yet. Galileo hasn't built his telescope. Newton won't be born for another 50 years. Every star in the night sky is a time capsule broadcasting history. The farther the star, the older the news. The center of our galaxy, the Milky Way's core, sits 26,000 light-years away. We observe it as it existed 26,000 years ago, during the last ice age, when humans were still hunter-gatherers, painting caves in France and Spain. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years distant. The light you see from Andromeda departed that galaxy 2.5 million years ago, when Australopithecus africanus walked Africa, when our genus Homo didn't exist yet, when Earth's climate was warmer, and Africa's jungles extended much farther than today, and we're just getting started. The most distant galaxy ever observed, designated HD, one discovered in 2022 using the Hubble Space Telescope and confirmed with other instruments, sits 13.5 billion light-years away. 13.5 billion light-years. The light we detect from HD1 began its journey when the universe was only 300 million years old, 2% of its current age. We're observing HD1 as it appeared just after the first stars ignited when galaxies were tiny compared to today's giants when the universe was still in its infancy. We're seeing HD1's baby pictures. We have no idea what HD1 looks like now. The light showing its present state won't reach us for another 13.5 billion years, nearly as long as the universe has currently existed. This is the first fundamental truth of cosmic scale: distance equals time. Space and time are inseparable. The farther you look, the farther back you see. The universe is a time machine built from the speed of light and the vast chasms between objects. But those chasms, those empty spaces, are about to get incomprehensibly larger. Neptune orbits 4.5 billion kilometers from the Sun, 30 times Earth's distance. Light from our star requires 4 hours to reach Neptune's frozen clouds. Voyager 2, launched in 1977, took 12 years to reach Neptune, arriving in 1989 after a journey using gravitational assists from Jupiter, Saturn, and Uranus. Without those gravity boosts, the trip would have consumed decades more. But Neptune doesn't mark the edge of our solar system, not remotely close. Beyond Neptune lies the Kuiper Belt, a disc-shaped region of icy bodies extending from 30 astronomical units to roughly 50 astronomical units. Pluto orbits here, taking 248 Earth years to complete one lap around the Sunday. Short period comets, those that return every few decades or centuries, originate from the Kuiper Belt, occasionally getting knocked inward by gravitational interactions. Beyond the Kuiper Belt stretches the scattered disk, reaching perhaps 100 astronomical units, populated by objects in highly elliptical orbits. And beyond that, far, far beyond, lies the Oort cloud. The Oort cloud is a spherical shell of trillions of icy bodies surrounding our entire solar system. Astronomers have never directly observed the Oort cloud. It's too distant, too dark, its objects too small, and spread too thinly. But we know it exists because long-period comets, those that take thousands or millions of years to orbit, arrive from all directions with orbits suggesting they originated from a spherical distribution. The Oort cloud begins around 2,000 astronomical units from the Sun, 2,000 times Earth's distance. Its outer edge extends somewhere between 100,000 and 200,000 astronomical units, possibly as far as 3.2 light-years from the Sunday. 3.2 light-years. That's 75% of the distance to Proxima Centauri, our nearest stellar neighbor. The Sun's gravitational influence reaches almost to the next star. Our solar system isn't a compact collection of 8 planets. It's a vast sphere, 3 light-years across, containing trillions of frozen bodies, most of which take millions of years to complete one orbit. An object at the Oort cloud's outer edge, orbiting at 3 light-years distance, requires approximately 30 million years per orbit. The last time one of these objects occupied its current position, Homo sapiens didn't exist. Our genus Homo had just evolved in Africa. Our ancestors were primitive hominins, learning to make stone tools competing with saber-toothed cats and giant hyenas. When that object completes its current orbit and returns to this position 30 million years from now, humans will be extinct or evolved beyond recognition. Continents will have drifted to new configurations. The night sky will display different constellations because nearby stars will have moved. This is our neighborhood. This 3-light-year sphere of frozen debris, barely held by the sun's weakening gravity. And between our neighborhood and the next, between the outer Oort cloud and Proxima Centauri's system, stretches 1.2 light-years of absolutely nothing. 1.2 light-years equals 11 trillion. 350 billion kilometers of pure vacuum. No planets, no asteroids, no comets, no dust, no gas atoms, nothing. Just empty space and occasional stray hydrogen atoms, maybe 1 atom per cubic centimeter. This gap is typical. In our region of the galaxy, the Orion Arm average stellar separation measures about 5 light-years. 5 light-years of emptiness between island systems of light. But some stars cluster more tightly. In the Trapezium cluster, a young star-forming region in the Orion Nebula, 1,344 light-years away, thousands of stars pack into a region just a few light-years across. These stars are so young, only a few 100,000 years old, that they haven't had time to drift apart yet. In a few million years, they'll spread out, and the cluster will dissolve. Globular clusters pack even tighter. Omega Centauri, the largest globular cluster orbiting the Milky Way, contains approximately 10 million stars crammed into a sphere 230 light-years across. At the cluster's core, stars average just 0.1 light-years apart, 30 trillion kilometers, roughly the distance from our Sun to the inner Oort cloud. If Earth orbited a star in Omega Centauri's core, the night sky would contain thousands of stars brighter than Sirius appears to us. Some would be bright enough to read by. The sky would never truly darken, always illuminated by countless nearby suns. But Omega Centauri is an exception, a relic from an earlier era of the universe when star formation proceeded more violently. The rule is emptiness. Our galaxy contains between 200 billion and 400 billion stars spread across 100,000 light-years. That sounds crowded until you calculate density. If you scaled the Milky Way so that Earth's orbit measured 1 millimeter across, the average distance between stars would still measure 30 meters. 30 meters of empty vacuum separating millimeter-wide solar systems. Even in our cosmic city, our galaxy of hundreds of billions of suns, we're profoundly alone, separated by gulfs so vast that even light requires years to cross from one star to the next. The Milky Way is a barred spiral galaxy. It has a central bar-shaped structure made of densely packed stars, with spiral arms curving outward from the bar's ends. We know this not from looking at the Milky Way from outside, we're embedded inside the disk, but from painstakingly mapping stellar positions and velocities. The European Space Agency's Gaia satellite, launched in 2013, has revolutionized our understanding of the galaxy's structure. Gaia measures the precise positions, distances, and motions of stars, using parallax, observing how nearby stars appear to shift against distant background stars as Earth orbits the Sunday. By 2022, Gaia had catalogued 1.8 billion stars, less than 0.5% of all stars in the galaxy, but enough to map galactic structure in unprecedented detail. The Milky Way rotates, but not as a solid disk. Different regions orbit at different speeds, creating a differential rotation pattern. Our Sun, positioned 26,000 light-years from the galactic center, orbits at 220 kilometers per second, nearly 1 million kilometers per hour. At that velocity, we complete one full orbit every 225 to 250 million years. Astronomers call this a galactic year or cosmic year. The last time our Sun occupied this exact position in galactic orbit, Earth was experiencing the Permian-Triassic extinction, the worst mass extinction in our planet's history. 96% of marine species and 70% of terrestrial vertebrate species went extinct. The cause remains debated, possibly massive volcanic eruptions in Siberia, possibly an asteroid impact, possibly a combination of catastrophes. Dinosaurs didn't exist yet, mammals didn't exist, flowering plants didn't exist. The supercontinent Pangaea was just forming, bringing all Earth's landmasses together into one giant continent. One galactic year, from now 250 million years, in the future Earth, will be unrecognizable. Plate tectonics will have rearranged continents into entirely new configurations. The sun will shine 5% brighter. Ocean chemistry will have changed. Whatever species dominate Earth won't be human. Homo sapiens will be as ancient and extinct as trilobites are to us now. But our orbit isn't smooth. As we travel around the galactic center, we oscillate up and down through the galactic plane like a sine wave. We bob above the disk, then sink below it, then rise again with a period of approximately 70 million years. Currently, we're about 70 light-years above the galactic plane, moving upward at 7 kilometers per second. In about 30 million years, we'll reach maximum height about 250 light-years above the plane, then fall back down, crossing through the plane, sinking below it, then rising again. Some researchers have proposed that these oscillations might correlate with mass extinctions on Earth. The idea is that passing through the denser galactic plane exposes our solar system to more cosmic rays, or gravitational perturbations might disturb the Oort cloud, sending showers of comets toward the inner solar system. The evidence for this correlation is controversial and far from proven. But the oscillation itself is real, confirmed by measuring our vertical velocity relative to the galactic disk. At the Milky Way's center, 26,000 light-years away, hidden behind vast clouds of dust that block visible light, sits Sagittarius A star, a supermassive black hole containing 4.1 million times the Sun's mass. 4.1 million solar masses compressed into a region about 17 times the Sun's diameter. That's roughly 25 million kilometers across, smaller than Mercury's orbit around the Sunday. How do we know Sagittarius A star is a black hole? Because astronomers at the Max Planck Institute for Extraterrestrial Physics in Germany spent 27 years, from 1992 to 2019, tracking individual stars orbiting it, using the Very Large Telescope in Chile and the Keck Observatory in Hawaii. They measured the positions of stars near the galactic center with extraordinary precision. One star designated S2 orbits Sagittarius A star with a period of 16 years in a highly elliptical orbit. At closest approach, called periapsis S2, comes within 1,400 astronomical units of Sagittarius A star. That's 1,400 times Earth's distance from the Sun. Close enough that the star's velocity reaches 7,650 kilometers per second, 2.55% of light speed. By tracking S2's orbit year after year, astronomers measured relativistic effects predicted by Einstein's general relativity gravitational redshift, where light loses energy climbing out of the black hole's gravitational well, and orbital precession, where the orbit's ellipse rotates over time. The measurements matched Einstein's predictions, perfectly confirming both general relativity and the existence of a 4 million solar mass object compressed into a tiny volume. The only thing that massive and compact is a black hole. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. The image shows a ring of glowing gas orbiting the black hole at velocities approaching light speed with a dark center, the shadow cast by the event horizon itself. The event horizon, the point of no return, has a diameter of about 24 million kilometers for Sagittarius A star. Once anything crosses that boundary, escape becomes impossible. Not difficult. Impossible. Even light moving at 300,000 kilometers per second aimed directly away from the black hole cannot escape. Inside the event horizon, space-time itself flows toward the singularity faster than light can move through it. Escape isn't a matter of going fast enough. It's geometrically impossible. Every direction you can point, including up, leads deeper into the black hole. At the singularity, the black hole's center general relativity predicts infinite density and infinite space-time curvature. The equations break down, physics as we know it stops working, We don't know what happens at a singularity. We can't know until we develop a theory of quantum gravity that reconciles general relativity with quantum mechanics. Sagittarius A star is currently quiet. It's not actively feeding on large amounts of matter. Occasionally, it consumes a gas cloud or an unlucky star that wanders too close, producing a brief flare of X-rays detectable by satellites. But mostly, it sits dormant, a silent monster at our galaxy's heart. This is common for supermassive black holes in the present-day universe. Most are quiescent. But in the early universe, 10 to 13 billion years ago, many were actively feeding, shining as quasars, so luminous they outshone their entire host galaxies by factors of hundreds or thousands. The brightest known quasar discovered in 2015 and designated SDSS J 0100+2802 has a luminosity 420 trillion times the Sun's output. It's powered by a black hole containing 12 billion solar masses, 12 billion times our Sun's mass accreting matter at a ferocious rate. That quasar sits 12.8 billion light-years away. The light we see from it left when the universe was only 900 million years old, 6.5% of its current age. The existence of 12 billion solar mass black holes, when the universe was less than 1 billion years old, presents a major puzzle in astrophysics. Black holes grow by accreting matter or merging with other black holes, but both processes take time. How do you grow a black hole to 12 billion solar masses in only 900 million years? One theory suggests these supermassive black holes formed from seeds, either the collapse of supermassive stars in the early universe, weighing hundreds or thousands of solar masses, or from dense star clusters that collapse directly into black holes. But we don't have definitive answers yet. The James Webb Space Telescope, launched in 2021, is now observing the early universe in infrared wavelengths, searching for clues about how these monster black holes formed so quickly. But here's what we do know with certainty: every large galaxy appears to have a supermassive black hole at its center. The Andromeda Galaxy's black hole contains 100 million to 200 million solar masses. The giant elliptical galaxy, Messier 87, 55 million light-years away, hosts a black hole of 6.5 billion solar masses. That's the black hole the Event Horizon Telescope photographed first in April 2019. The image shows a ring of glowing gas orbiting a dark shadow, direct visual evidence of a black hole's event horizon. These supermassive black holes aren't just passengers in their galaxies. They shape galactic evolution. When they feed actively, when matter spirals into them, they release enormous amounts of energy as jets and radiation. These outflows can heat gas throughout the galaxy, preventing it from cooling and collapsing to form new stars. The black hole regulates star formation across the entire galaxy. Astronomers have discovered a correlation between a galaxy's supermassive black hole mass and the velocity dispersion of stars in the galaxy's central bulge. Larger, more massive galaxies have more massive black holes. The ratio is remarkably consistent. The black hole's mass is typically 0.1% of the bulge's mass. This suggests black holes and galaxies co-evolve, growing together over billions of years through complex feedback mechanisms we're still working to understand. Our Milky Way will undergo dramatic changes in the future. In about 4 billion years, the Milky Way and Andromeda will collide. The two galaxies are currently approaching each other at approximately 110 kilometers per second. When I say collide, I don't mean stars will smash into each other. Stars are so small and so far apart that even when two galaxies merge, individual stellar collisions are statistically impossible. The galaxies will pass through each other like ghosts, but gravity will wreak havoc. The two galaxies will distort each other's shapes, pulling out long tidal tails of stars stretching hundreds of thousands of light-years into space. Gas clouds will collide and compress, triggering massive bursts of star formation across both galaxies. Millions of new stars will ignite over a few 100 million years. The supermassive black holes at the centers of both galaxies, 4 million solar masses from the Milky Way, 100 million to 200 million from Andromeda, will spiral toward each other, eventually merging into a single black hole of roughly 104 million to 204 million solar masses. The merger will take about 2 billion years from first contact to final configuration. The result, a massive elliptical galaxy roughly twice the size of either original galaxy. Astronomers have already named it Milky Way. Computer simulations of this merger, run by astrophysicists at Harvard-Smithsonian Center for Astrophysics and other institutions, predict that our solar system will probably survive intact. We'll likely be flung to a different orbital radius, maybe closer to the merged galaxy's center, maybe farther out, but the sun and planets should remain bound together. If any intelligent species exists on Earth 4 billion years from now, and that's a big if, given that Homo sapiens has only existed for 300,000 years, they'll witness a spectacular sky. During the merger's peak, the night sky will blaze with newly formed stars, glowing nebulae, and gravitational chaos as two galactic cores spiral around each other. But humans almost certainly won't see it. In about 1 billion years, long before the Andromeda collision, the Sun's luminosity will increase by about 10% due to changes in its core structure as it ages. That's enough to trigger a runaway greenhouse effect on Earth. Oceans will evaporate. Water vapor in the atmosphere will trap more heat. Surface temperatures will climb past 100 degrees Celsius, then 200, then higher. Earth will become Venus, a scorched hellscape with a crushing carbon dioxide atmosphere and surface temperatures hot enough to melt lead. Life on Earth, unless it evacuates to other worlds, will end. In 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core. The Sun will expand into a red giant swelling to perhaps 200 times its current diameter. It will likely engulf Mercury and Venus. Earth might survive at the edge of the Sun's expanded atmosphere, but it will be a charred, lifeless cinder, all atmosphere stripped away, all water gone surface, molten. Eventually, the Sun will shed its outer layers in a planetary nebula, a glowing shell of gas expanding into space, leaving behind a white dwarf about the size of Earth but containing 60% of the Sun's current mass. That white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder invisible against the void. This is the fate of all sun-like stars, and it's happening to stars across the galaxy right now. The Milky Way creates about 1.5 new stars per year, on average, but the star formation rate is declining. In the early universe, galaxies formed stars at rates 10 to 100 times higher than today. We're running out of raw material. Hydrogen gas, the fuel for star formation, is being consumed faster than it's replenished. Much of the galaxy's gas has already been locked up in long-lived stars, or blown out of the galaxy entirely by supernova explosions and stellar winds. In 10 trillion years, star formation in the Milky Way will essentially cease. The last new stars will ignite. After that, the galaxy will contain only aging stars slowly burning through their remaining fuel. The universe is winding down. Entropy is increasing. The age of stars won't last forever, but we're not there yet. We're still in the golden age, the brief cosmic window, when stars shine, when galaxies dance, when life is possible. And we're about to see just how crowded or empty the rest of the universe really is. The Milky Way is one galaxy among 2 trillion in the observable universe. 2 trillion. 2 million galaxies, each containing hundreds of billions of stars, scattered across 93 billion light-years of space. But they're not distributed evenly. Galaxies cluster into groups and clusters, and those clusters organize into superclusters, and those superclusters arrange themselves along vast filaments surrounding cosmic voids. Regions of space where almost nothing exists. This is the cosmic web, the largest scale structure in the universe. Let me build this structure from the bottom up. Our Milky Way belongs to the local group, a collection of about 80 galaxies within a 10 million light-year diameter region. The 3 largest members are the Milky Way, Andromeda, and Triangulum Galaxy. Triangulum contains about 40 billion stars and sits about 3 million light-years away. The rest of the local group consists of dwarf galaxies, small collections of a few million to a few billion stars orbiting the larger galaxies like satellites. The Large Magellanic Cloud and Small Magellanic Cloud, visible from Earth's southern hemisphere, are dwarf galaxies orbiting the Milky Way at about 160,000 and 200,000 light-years distance, respectively. These dwarf galaxies are slowly being cannibalized by the Milky Way. Over billions of years, tidal forces will tear them apart, and their stars will be absorbed into our galaxy. This process is already underway. The Sagittarius dwarf elliptical galaxy is currently being shredded by the Milky Way's gravity, leaving a stream of stars wrapping around our galaxy like a ribbon. This is how large galaxies grow, by consuming smaller neighbors. The Milky Way has absorbed dozens of dwarf galaxies over its history. Evidence appears in stellar streams, rivers of stars with similar ages and compositions, tracing the orbits of long-dead dwarf galaxies, torn apart millions or billions of years ago. Zooming out from the local group, we're part of the Virgo supercluster, a massive structure containing at least 100 galaxy clusters spread across 110 million light-years. The Virgo supercluster contains roughly 100,000 large galaxies and perhaps trillions of dwarf galaxies. At the Virgo supercluster's heart sits the Virgo cluster, a dense collection of about 1,500 galaxies concentrated in a region about 15 million light-years across. The largest galaxy in the Virgo cluster is Messier 87, the giant elliptical galaxy whose supermassive black hole was photographed in 2019. But even the Virgo supercluster isn't the full picture. In 2014, a team led by astronomer Brent Tully at the University of Hawaii published a paper mapping the motion of galaxies in our region of space, using redshift surveys and distance measurements. They discovered that the Virgo supercluster, along with dozens of other superclusters, are all flowing toward a common gravitational basin, pulled by the combined gravity of all matter in that direction. They named this structure Laniakea, meaning immeasurable heaven in Hawaiian. Laniakea is a supercluster of superclusters containing about 100,000 large galaxies spread across 520 million light-years. Our entire local group, the Virgo supercluster, the Hydra Centaurus supercluster, the Pavo Indus supercluster, and dozens of others are all part of Laniakea, all flowing along gravitational channels toward a region called the Great Attractor. The Great Attractor is a gravitational anomaly 220 million light-years away, hidden behind the Milky Way's galactic plane in an area called the Zone of Avoidance. Dust in our galaxy blocks visible light from that direction, making the Great Attractor impossible to observe directly with optical telescopes. But radio and infrared observations can penetrate the dust. Using these wavelengths, astronomers have detected a massive concentration of galaxies, the Norma cluster, at the Great Attractor's location, containing the mass of tens of thousands of galaxies. And the Great Attractor itself appears to be flowing toward an even larger structure, the Shapley supercluster, located 650 million light-years away. The Shapley supercluster is the largest concentration of galaxies in the nearby universe, containing more than 8,000 galaxies, with a total mass of about 10 quadrillion solar masses. 10 quadrillion, 10 million, billion times the Sun's mass. This is the cosmic web at work, a hierarchy of structures pulling on each other through gravity, creating flows and currents of galaxies across hundreds of millions of light-years. But between these structures, between the filaments and superclusters, lie voids. Cosmic voids are vast regions of space where almost no galaxies exist. The Boötes void, discovered in 1981 by Robert Kirshner and colleagues, spans approximately 330 million light-years across and contains only about 60 galaxies. 330 million light-years, with only 60 galaxies. Normal cosmic density would predict 10,000 galaxies in that volume. The Boötes void contains 99.4% fewer galaxies than expected. If you were somehow transported to the center of the Boötes void, you wouldn't see a single galaxy in any direction. Just darkness. Utter, absolute darkness. No stars, no nebulae, no galaxies, just the faint glow of the cosmic microwave background radiation. The largest known void is the KBC void, named after astronomers Keenan Barger and Cowie, who identified it in 2013. Earth appears to be located near the center of this void, which spans approximately 2 billion light-years. We're not at the center of the universe. There is no center. The universe has no edge or central point, but we do happen to sit in an unusually empty region of space. This might partially explain some cosmological measurements. If we're in an underdense region, the expansion rate we measure from our location might differ slightly from the average expansion rate across the entire universe. This is one proposed explanation for the Hubble tension, a discrepancy between different methods of measuring the universe's expansion rate. Some methods give a value of about 67 kilometers per second per megaparsec. Other methods give about 73 kilometers per second per megaparsec. The difference might seem small, but it's statistically significant and has persisted despite increasingly precise measurements. Either there's systematic error in one or both measurement methods, or there's new physics we don't understand. Or possibly, we're in a local void, and that affects our measurements. The issue remains unresolved. But back to structure. How did the cosmic web form? It started with quantum fluctuations in the first fraction of a second after the Big Bang. At 10 to the power of negative 30, 6 seconds after time began. That's
0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 cosmic inflation. During inflation, the universe expanded by at least a factor of 10 to the power of 26, growing from smaller than an atom to at least 10 centimeters across, in less than 10 to the power of negative 32 seconds. This sounds absurd. It is absurd, but we have evidence. Cosmic inflation was proposed in 1980 by physicist Alan Guth to solve several problems in cosmology: the horizon problem, the flatness problem, and the monopole problem. The theory makes specific predictions about the universe's structure, and those predictions have been confirmed by observations. During inflation, quantum fluctuations, tiny random variations in energy density at subatomic scales, were stretched to cosmic sizes. These fluctuations became regions of slightly higher and slightly lower density in the primordial universe. Regions with higher density had slightly stronger gravity. They attracted more matter. Regions with lower density had weaker gravity. They lost matter to their denser neighbors. Over hundreds of millions of years, gravity amplified these tiny differences. Dense regions grew denser, forming protogalaxies and eventually galaxy clusters. Underdense regions grew emptier, forming voids. We have direct evidence of these initial fluctuations. The cosmic microwave background radiation, the afterglow of the Big Bang emitted when the universe was 380,000 years old, shows temperature variations of about 1 part in 100,000 across the sky. These temperature variations, first detected by NASA's COBE satellite in 1992 and mapped in exquisite detail by the Planck satellite in 2013, correspond exactly to the density fluctuations that seeded cosmic COBE's structure. In the cosmic microwave background map, slightly warmer regions represent slightly denser areas that became galaxy clusters. Slightly cooler regions represent slightly less dense areas that became voids. You can trace the lineage of every galaxy, every star, every planet back to quantum fluctuations in the first fraction of a second after the Big Bang. The universe's largest structures, superclusters, spanning hundreds of millions of light-years, originated as quantum fluctuations smaller than an atom stretched to cosmic scales by inflation, then amplified by gravity over 13.8 billion years. This is one of the most profound discoveries in cosmology. The universe is connected across all scales from quantum to cosmic, from the first instant to the present day. Computer simulations of cosmic structure formation run by teams at institutions like the Max Planck Institute for Astrophysics confirm this picture. Researchers input the initial density fluctuations measured in the cosmic microwave background, apply known physics, gravity, gas dynamics, dark matter, and evolve the simulation forward billions of years. The results match the observed cosmic web in stunning detail. Simulations produce filaments, walls, clusters, and voids with the same statistical properties as the real universe. This is powerful confirmation that we understand how structure formed, but simulations reveal something else. Visible matter, atoms, stars, gas, planets, makes up only about 5% of the total matter in the universe. The other 95% is dark. 27% is dark matter that doesn't emit, absorb, or reflect light, but has gravitational effects we can measure. Dark matter provides the gravitational scaffolding on which galaxies form.
Without dark matter, galaxies as we know them couldn't exist. 68% is dark energy, a mysterious component that acts like anti-gravity, causing the universe's expansion to accelerate. We know dark energy exists because we've measured the acceleration, but we have no idea what it actually is. 95% of the universe is invisible to us directly. We detect it only through gravitational effects and expansion measurements. Dark matter reveals itself through gravitational lensing, the bending of light by gravity. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends the light path, creating distorted, stretched images of the background galaxy. By measuring these distortions, astronomers can map dark matter's distribution. The result, dark matter forms vast halos around galaxies and clusters with visible matter concentrated at the centers. Dark matter outweighs visible matter by about 5-1. Some clusters show even more dramatic lensing. The Bullet cluster, formed by the collision of two galaxy clusters, about 3.8 billion light-years away, provides some of the strongest evidence for dark matter's existence. When the clusters collided, the hot gas, which makes up most of the visible matter, slammed together and was slowed by electromagnetic forces. But dark matter, which interacts only through gravity, passed right through. Gravitational lensing measurements show that most of the mass is now separated from the visible gas, proving that some form of non-luminous matter exists. What is dark matter? We don't know. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical subatomic particles that don't interact via electromagnetic force. Despite building ultra-sensitive detectors deep underground to shield them from cosmic rays, physicists haven't detected WIMPs yet. Other candidates include axions, sterile neutrinos, or more exotic possibilities. Or perhaps our understanding of gravity at large scales is wrong, and what we interpret as dark matter is actually a modification of gravitational physics. But modified gravity theories struggle to explain all the observations that dark matter explains naturally. This is one of the biggest unsolved problems in physics. 95% of the universe is made of things we don't understand, but we can map them. We can measure their effects. And what we've found is that the universe has structure at every scale, from planets to stars, to galaxies, to clusters, to superclusters, to the cosmic web itself. And all of this, all 2 trillion galaxies, all the filaments and voids, all the dark matter and dark energy exists within a sphere 93 billion light-years across. The observable universe. But why observable? Why is there a limit? Why can't we see farther? Because there's a horizon. A boundary beyond which light has not had time to reach us since the Big Bang. And that horizon is about to reveal the most mind-bending aspect of cosmic scale. The observable universe is a sphere, 93 billion light-years in diameter, centered on Earth. Wait. The universe is 13.8 billion years old. Light has had 13.8 billion years to travel since the Big Bang. Shouldn't the observable universe be only 13.8 billion light-years in radius, 27.6 billion light-years across? No, because space itself has been expanding while that light traveled toward us. This is the key to understanding cosmic horizons, and it breaks most people's intuition completely. Imagine a photon emitted from a distant galaxy 13.7 billion years ago, when the universe was only 100 million years old, less than 1% of its current age. That photon begins traveling toward us at 300,000 kilometers per second, the speed of light. But space is expanding. As the photon crosses space, more space is being created behind it and in front of it. The photon is still moving at light speed relative to the space immediately around it, but the destination Earth is receding because space between the photon and Earth is stretching. It's like running on a treadmill that's accelerating. You're running at constant speed relative to the belt, but the finish line keeps getting farther away. Eventually, after 13.7 billion years of travel, the photon reaches Earth. Mission accomplished. But during those 13.7 billion years, space expanded. The galaxy that emitted that photon, which was much closer when the photon started, has been carried away by expanding space and is now 46 billion light-years distant. The photon's journey was 13.7 billion light-years through space, but the starting point is now 46 billion light-years away. because space expanded during the journey. This happens in all directions. We can see light from galaxies up to 46 billion light-years away in every direction, creating an observable sphere 93 billion light-years across. Astronomer Ned Wright at UCLA has calculated this precisely using the standard cosmological model. The math is complex, involving general relativity and the expansion history of the universe. But the result is clear. The observable universe is 93 billion light-years across, containing approximately 2 trillion galaxies. And this is crucial, there's almost certainly more universe beyond that sphere. Probably much more. Possibly infinitely more. We just can't see it. We never will. There's a horizon, the cosmic horizon or particle horizon, beyond which light has not had enough time to reach us since the Big Bang. No matter how long we wait, light from beyond that horizon will never arrive, because space is expanding, and at great enough distances, it's expanding faster than light can cross it. This doesn't violate special relativity. Nothing is moving through space faster than light. Space itself is expanding, carrying galaxies along with it, and that expansion has no speed limit. Think of it this way: imagine ants walking across the surface of an inflating balloon. Each ant walks at constant speed relative to the rubber immediately under its feet, but ants on opposite sides of the balloon are separating faster than either ant is walking because the rubber between them is stretching. That's what's happening in the universe. Galaxies aren't flying through space, space is expanding, carrying galaxies with it. In 1929, astronomer Edwin Hubble discovered this expansion by measuring the distances and velocities of nearby galaxies using the 100-inch telescope at Mount Wilson Observatory. He found that distant galaxies are moving away from us, and the farther a galaxy is, the faster it recedes. This relationship is now called Hubble's law. Velocity equals the Hubble constant times distance. The Hubble constant, usually written h0, tells you how fast the universe is expanding. Current measurements put it at about 67 to 73 kilometers per second per megaparsec, depending on which measurement method you use. A megaparsec is about 3.26 million light-years. So the Hubble constant means that for every 3.26 million light-years of distance, recession velocity increases by 67 to 73 kilometers per second. A galaxy 10 megaparsecs away recedes at about 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second. At some distance, about 14 billion light-years in the current era, recession velocity equals the speed of light. At greater distances, recession velocity exceeds light speed. This is allowed. Special relativity prohibits moving through space faster than light, but it says nothing about space itself expanding. Galaxies beyond this distance are receding faster than light. Light emitted from those galaxies toward us is still traveling at light speed locally, but it's fighting a losing battle against expanding space. The light is making progress toward us, but the finish line is receding faster than the light can catch up. For galaxies far enough away, light emitted today will never reach us. Ever. The space between us and them is expanding too fast. Those galaxies are beyond our cosmic horizon. They're causally disconnected from us. We can never interact with them. They can never interact with us. No information can be exchanged. And here's the disturbing part. The horizon is shrinking. In 1998, two teams of astronomers studying distant Type Ia supernovae, Saul Perlmutter's Supernova Cosmology Project, and Brian Schmidt and Adam Rees's High Z Supernova Search Team made a shocking discovery. They were measuring supernovae at various distances to map the expansion history of the universe. Everyone expected to find that the expansion was slowing down due to gravity. The question was whether it was slowing down enough to eventually reverse and cause a big crunch, or whether the universe would expand forever, but at a decreasing rate. Instead, they found acceleration. The universe's expansion is speeding up. This was so unexpected that both teams spent months checking for errors before publishing. But the result held up. The universe's expansion is accelerating, and it's been accelerating for about the last 6 billion years. Something is pushing space apart at increasing rates. We call it dark energy, and it makes up about 68% of the total energy density of the universe. But we have no idea what it actually is. The simplest explanation is that dark energy is the cosmological constant, a property of space itself representing the energy of the vacuum. Einstein introduced the cosmological constant in 1917, then later called it his biggest blunder when Hubble discovered the universe was expanding. But it turns out the cosmological constant might be real after all. If dark energy is the cosmological constant, its density remains constant as space expands. But the total amount of dark energy increases because there's more space. Meanwhile, matter density decreases as space expands the same amount of matter spread over a larger volume. So, as the universe ages, dark energy becomes increasingly dominant, causing expansion to accelerate more and more. This has profound implications for the future. Currently, we can see approximately 2 trillion galaxies, but galaxies at the edge of our observable sphere are receding at nearly the speed of light due to expansion. As expansion accelerates, more and more galaxies will cross the cosmic horizon and disappear from view. Their light will be redshifted to longer and longer wavelengths, from visible to infrared to microwave to radio, until finally the wavelength becomes infinite and the light vanishes entirely. In about 150 billion years, all galaxies beyond our local group will have crossed the horizon and disappeared. Future astronomers will look up and see only the merged Milky Way, Andromeda Galaxy, Milkomeda, surrounded by empty darkness. They'll have no evidence that other galaxies ever existed. No cosmic microwave background radiation. It will have redshifted to undetectable wavelengths. No evidence of the Big Bang. No expansion to measure. No way to deduce cosmic history. They'll be cosmologically blind, living in a universe that has hidden its own past. We are living in a privileged era. Right now, 13.8 billion years after the Big Bang, the universe is still young enough, still close enough together that we can see its full structure and history. We can detect the cosmic microwave background radiation emitted 380,000 years after the Big Bang and study the universe's infancy. We can see galaxies at distances of 13.5 billion light-years, observing them as they appeared when the universe was only a few 100 million years old. We can map the cosmic web across billions of light-years. We can measure the expansion rate and trace cosmic history from the first fraction of a second to the present day. Future civilizations won't have this privilege. The universe will have erased the evidence of its own origins. But we're here now in this brief window of cosmic clarity, when the universe is revealing its secrets. And the most profound secret is this: the observable universe is just a bubble. Beyond our 93 billion light-year sphere lies more universe, possibly infinite universe, that we can never see, never study, never know. The universe could be infinite in extent. It could be finite but larger than the observable portion. It could wrap around on itself in higher dimensions, like the surface of a four-dimensional hypersphere. We don't know. We can't know. The information is permanently sealed away, beyond the cosmic horizon. This is one of the hardest limits in science. There are fundamental questions about reality we cannot answer, not because our technology is insufficient, but because the information cannot physically reach us. The speed of light and the expansion of space create an information boundary we can never cross. But within our observable bubble, within the 93 billion light-year sphere, we can study. We've learned extraordinary things about the universe's structure, history, and future. And we've discovered something unexpected about time itself. The universe has an age and it's temporary. The cosmos won't look like this forever. The age of stars, the era we're living in now, is finite. It will end. And when it ends, the universe will become something utterly alien, a cold, dark, empty void stretching into eternity. Let me show you the timeline of cosmic death. The universe is 13.8 billion years old. Stars will continue forming and shining for approximately another 100 trillion years. 100 trillion years. That's 7,000 times longer than the current age of the universe. It sounds like forever. It's not. Right now, this moment in cosmic history, we're living in the stelliferous era, the age of stars. This era began about 200 million years after the Big Bang, when the first stars ignited from collapsing clouds of primordial hydrogen and helium. Those first stars were massive, perhaps 100 to 1,000 times the Sun's mass, and they burned hot and fast, exhausting their fuel in just a few million years before exploding as supernovae. Those explosions scattered heavy elements into space: carbon, oxygen, nitrogen, silicon, iron. Second-generation stars formed from gas, enriched with these heavy elements. They were more diverse, some large, some small, some sun-like. And when they died, they scattered even more heavy elements into space. Our Sun is a third-generation star, at minimum, possibly fourth or fifth generation. We know this because the Sun contains heavy elements. About 2% by mass is stuff heavier than helium. Those elements came from previous generations of stars that lived, died, and enriched the galaxy's gas. Right now, star formation in the Milky Way proceeds at about 1.5 solar masses per year, roughly one Sun-like star forms annually, or several smaller stars. That's down from peak star formation rates billions of years ago. In the early universe, 10 to 13 billion years ago, galaxies formed stars at rates 10 to 100 times higher than today. The universe is running out of raw material. Hydrogen gas, the fuel for star formation, is being consumed. Some gets locked into long-lived stars. Some gets expelled from galaxies by supernova explosions and stellar winds. Some falls into black holes. The reservoir is being depleted. In 10 trillion years, star formation will have declined to a trickle across the universe. In 100 trillion years, the last new stars will ignite small red dwarfs, the smallest possible self-sustaining stars, weighing just 8% of the Sun's mass. Red dwarfs are the universe's marathon runners. They burn hydrogen so slowly, so efficiently, that they can shine for trillions of years. The smallest red dwarfs can last 10 trillion years or more. When the last red dwarf finally exhausts its hydrogen fuel and fades to a cold black dwarf, a stellar corpse radiating only residual heat, the stelliferous era ends. Then comes the degenerate era. In this era, the universe contains no living stars, only stellar corpses, white dwarfs, neutron stars, and black holes. White dwarfs, the remnants of Sun-like stars, are Earth-sized objects containing about half to 1.4 solar masses. They're incredibly dense. 1 teaspoon of white dwarf material weighs about 15 tons on Earth. White dwarfs don't generate energy through fusion. They just sit there slowly radiating away their stored thermal energy. The process takes an incomprehensibly long time. Physicists have calculated that a white dwarf requires about 10 to the power of 32 years, 100 million trillion years to cool to near absolute zero. During the degenerate era, galaxies gradually dissolve. Stars, now dead, occasionally encounter each other gravitationally. Sometimes they exchange energy through a process called gravitational scattering. One star gains energy and speeds up, the other loses energy and slows down. Eventually, some stars gain enough energy to exceed the galaxy's escape velocity and fly off into intergalactic space, never to return. Over about 10 to the power of 19 years, 10 billion years, half of a galaxy's stars will be ejected this way. The remaining stars spiral inward, eventually falling into the central supermassive black hole. Meanwhile, planets spiral into their dead stars due to gravitational radiation ripples in spacetime predicted by general relativity and directly detected by the LIGO experiment in 2015. Gravitational radiation is extremely weak, but over long enough timescales, it has measurable effects. A planet like Earth orbiting a white dwarf will slowly lose orbital energy to gravitational waves and spiral inward. The process takes about 10 to the power of 20 years. Eventually, the planet crosses the white dwarf's surface and is absorbed, but the degenerate era doesn't last forever either. Around 10 to the power of 40 years from now, something even stranger happens. Protons decay. Protons, the positively charged particles in atomic nuclei. The building blocks of ordinary matter might not be truly stable. Most theories beyond the standard model of particle physics predict protons eventually decay into lighter particles, positrons, pions, photons. We've never directly observed proton decay. Experiments like Super Kamiokande in Japan, a tank containing 50,000 tons of ultra-pure water, surrounded by 11,000 photomultiplier tubes, buried 1 kilometer underground, have been searching for proton decay since 1996. So far, nothing. If protons decay, their half-life exceeds 10 to the power of 34 years, 100,000 trillion years, vastly longer than the current age of the universe. But given enough time, 10 to the power of 40 years or so, even that incredibly slow decay rate will disintegrate all matter. Atoms will fall apart. Planets dead, stars, asteroids, everything made of ordinary matter will dissolve into a diffuse gas of electrons, positrons, neutrinos, and photons. The only structures remaining will be black holes. This begins the black hole era. Black holes don't decay through proton decay, they're not made of protons, but they do decay through Hawking radiation. In 1974, Stephen Hawking showed that black holes aren't truly black. Due to quantum effects near the event horizon, black holes emit thermal radiation. They evaporate extremely slowly. Here's how it works in quantum field theory. Empty space isn't truly empty. Virtual particle-antiparticle pairs constantly pop into existence and annihilate each other everywhere, existing for tiny fractions of a second before disappearing. Normally, these quantum fluctuations have no macroscopic effect. But near a black hole's event horizon, something different happens. A particle-antiparticle pair appears just outside the event horizon. Before they can annihilate, one particle falls into the black hole while the other escapes into space. From an outside observer's perspective, the black hole emitted a particle. But energy is conserved. The black hole loses mass equal to the escaped particle's energy. The black hole evaporates one quantum particle at a time. The evaporation rate depends on the black hole's mass. Smaller black holes evaporate faster. Larger ones evaporate slower. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. That's a 1, followed by 67 zeros. A supermassive black hole, like Sagittarius. A star 4 million solar masses would take about 10 to the power of 99 years. 10 to the power of 99 years. This number is so incomprehensibly large that even writing it in standard notation is pointless. It's a 1 followed by 99 zeros. If you wrote 1 0 per second, it would take you 99 seconds to write the number. But the time period itself, there's no human reference point. Nothing to compare it to. It's just vast beyond any meaningful comprehension. But even this unimaginable span of time is finite. Eventually, after 10 to the power of 100 years, the last supermassive black holes evaporate in final bursts of Hawking radiation. Then comes the dark era. After 10 to the power of 100 years, the universe contains nothing but a thin gas of photons, electrons, positrons, and neutrinos spreading through infinite expanding space. No structure, no complexity, no stars, planets, atoms, or molecules. Nothing that could support chemistry, biology, or life as we know it. The temperature of the universe asymptotically approaches absolute zero minus 273.15 degrees Celsius. Energy becomes evenly distributed. There are no energy gradients, no differences in temperature or density anywhere. This is heat death first proposed by physicist Hermann von Helmholtz in 1854 and formalized by the second law of thermodynamics. The universe reaches maximum entropy, maximum disorder, and in that state nothing can happen. Ever. Again. No chemical reactions. Chemistry requires energy gradients. No motion. Movement requires force, which requires energy gradients. No change of any kind. Just an infinite expanse of ultra-cold particles drifting slowly apart as space expands forever. Eternal darkness. Eternal cold, eternal stillness. This is the universe's ultimate fate, according to our current understanding of physics, the Big Freeze. There are alternative scenarios. The Big Rip, where dark energy eventually grows strong enough to tear apart galaxies, then solar systems, then planets, then atoms, then even subatomic particles, and space-time itself. But current evidence suggests the Big Freeze is most likely. Now, let me put this timeline in perspective. If the universe's total lifespan was 1 year, here's how it would play out. The Big Bang occurs at midnight on January 1st. First stars form at 12:40 a.m. 40 minutes after midnight. Our Sun forms at 9 p.m. on August 30, first 2/3 through the year.
Complex life on Earth emerges at 11 p.m. on December 31st. Humans appear at 11:59:55 p.m. on December 31st, 5 seconds before midnight. All of human history, from first civilizations to now, occurs in the last half second before midnight. Midnight arrives. New Year begins. The last stars die at 6 a.m. on January 2nd, 6 hours into the new year. The rest of January, second darkness. All of February through December, darkness. And then every year after that, forever darkness. Stars shine for 6 hours in a year that lasts eternity. We exist in those 6 hours. We exist in the universe's brief morning when stars still burn and consciousness is possible. But here's what makes this timeline profound. We're not just living during the 6 hours when stars shine. We're living in the best possible moment within that 6-hour window. In the first few 100 million years after the Big Bang, the universe was too violent, too hot, too chaotic. No stable planetary systems could form. No long-lived stars to provide steady energy. The universe needed time to settle down, to cool, to build up reserves of heavy elements in multiple generations of stellar death. In 100 trillion years, all stars will be dead. No energy sources, no warmth, no possibility for complex chemistry or life as we know it. But right now, 13.8 billion years after the Big Bang, conditions are perfect. Stars are shining, providing stable energy sources for billions of years. Heavy elements exist, created in earlier stellar generations, making planets and complex chemistry possible. The universe has cooled enough for stable structures to form, but hasn't yet exhausted its fuel. And perhaps most remarkably, the cosmic microwave background radiation is still detectable. The expansion of the universe is still measurable. Evidence of the Big Bang still exists. We can study our cosmic origins, because we're close enough in time to the beginning to still see its effects. Future civilizations, trillions of years from now, if any exist, won't have this. They'll look up at a much darker, emptier universe with no evidence of its own history. We're living in a cosmologically privileged era, not because humans are special, but because consciousness can only exist in the narrow window when conditions permit, which happens to be the same window when the universe is most observable. Consciousness arose when the universe was old enough for complexity, but young enough for stars. And that raises the final question: what does it mean to be conscious in a universe this vast, this temporary, this ultimately doomed? What does it mean to be you, a thinking, feeling, being in all of this? You are made of atoms, forged in the cores of dying stars billions of years ago. The calcium in your bones created in a supernova. The iron in your blood from a different supernova. The oxygen in your lungs from another dying star. The carbon in your DNA built in the core of a red giant. Every atom heavier than hydrogen and helium in your body was created inside a star and scattered into space when that star died. This is literal truth confirmed by decades of astrophysical research. You are 13.8 billion years of cosmic evolution made conscious. You are stardust that learned to wonder about stars. You are the universe's way of knowing it exists. And you exist now during the universe's golden age when stars shine and consciousness can observe the cosmos, rather than in the endless dark eons before stars ignited or after they've all died. You are simultaneously insignificant and precious, tiny by spatial measure, smaller than a grain of sand on cosmic scales, but cosmically valuable by significance measure, one of the only parts of the universe that can think, feel, wonder, understand. The universe is 93 billion light-years across. You are about 1.7 meters tall. The universe is 13.8 billion years old. You'll live perhaps 80 years. The universe contains 200 billion trillion stars. You are one organism on one planet. By any spatial or temporal measure, you're nothing. But you're conscious. You can understand physics. You can trace your own atomic lineage back to the Big Bang. You can map the structure of the observable universe. You can contemplate your own insignificance and find meaning in it anyway. In all that vastness across all those trillions of galaxies, you are the exception. You are matter that thinks. You are the universe briefly aware of itself. And that awareness won't last forever. Not just your individual consciousness, though that will end,
But all consciousness everywhere might eventually cease when the universe reaches heat, death, and no energy gradients exist anymore. Or maybe we'll find a way to survive. Maybe consciousness will spread to other stars, other galaxies, becoming a cosmic civilization that outlasts the age of stars through technologies we can't imagine yet. We don't know, but right now consciousness exists. You exist. You can think, feel, wonder, love, create, understand. The universe spent 13.8 billion years, unconscious stars forming, burning, dying blindly before you appeared. And for this brief moment, the universe is awake in you. It's seeing through your eyes, thinking through your mind, feeling through your heart. That's the true scale of the universe. Not the billions of light years, though they're real. Not the trillions of galaxies, though they're out there. The true scale is the contrast infinite vastness containing infinitesimal consciousness. 200 billion trillion stars, and only one planet we know of where the universe can see itself. You are that planet. You are that consciousness. You are the universe temporarily awake. Make it count.